Alright, hey, it's Mr. K doing a video for AP Physics 2. We're going to do a video on capacitance and capacitors. Capacitors are charge storing devices, so by the name itself, it's going to have a capacity and it's going to have a capacity to hold charge. So a capacitor, in essence, is just two conductive sheets of metal, and it's going to be separated by a certain distance. And if it wasn't separated by the distance, then if we were to charge up one side, let's say positive, and the other side is negative, then if we were to touch these two sides together, then they would just discharge and you would no longer have a negative and a positive. You would have no charge stored anymore. It would just go back to neutral. So in essence, we have a capacitor. We have a parallel plate, one that's up here, one that's down there. One's going to be charged up positive, the other one's going to be charged up negative. And let's just talk about the physics of this. These two plates are going to want to attract to each other. And the geometry of a capacitor is going to be very important. There's something that we call capacitance. And it's going to be measured in farads. So we're usually going to work with the microfarad, but a farad is going to be F and the measurement of a capacitor. And the capacitance is really reliant upon several things. One is if you made these metal plates bigger, we would be able to store more charge. It's kind of, makes sense. So the surface area of these plates matters. And then the distance of separation also matters. This distance in between, D, is going to be the separation distance. As we bring these two plates closer and closer and closer together, there will be more attraction because of the lack of distance here now between these charged plates. And they're going to want to pull towards each other, which is actually going to make it easier for us to store more and more charge on here. As you dump charge onto one side, all those charges being the same charge, they want to get away from each other. And so in the case of capacitors, when you get really close, now you can utilize this force of attraction to keep the charges on there to put even more charges onto the parallel plates. So capacitance deals with the area of the plates and this distance that separates them. And so if we look at the area of these plates and the distance d, then the geometry is going to be very important here. And there's also going to be something called the permittivity of free space, which is going to be E naught. And there's also one more thing, which is going to be this thing called K, which is going to be the stuff that you're going to put in between here. So right now we just have air, but as we can fill this with certain materials that would be kind of like a decent insulator to prevent the charges from going across, which is going to allow us to move these even more and more closer. So the distance d could be even smaller without the charges jumping across if we had a good insulator in between. And so the capacitance would rely on the area of it, the distance between these plates. Permittivity of free space, this is a property of the universe, so permittivity of free space, there's a constant for that. And then K, this K value, kind of a kappa value, is whatever material you place in between. Alright, so again, this capacitor, to charge it up in the first place, we probably need to attach it to a battery, give it some reason to have charge. And let's put it to a battery here. And I'm going to attach the positive side, of course, to the positive side of the battery. Negative side to the negative side of the battery, and there's going to be some voltage to the battery as well. That voltage will be the same voltage difference here. So let's say that it is 100 volts. And so for these parallel plates, we would have a 100-volt difference between the two plates. And so just a little bit of electrostatics as well as the circuit element that we're going to be talking about. But we have positive charges and negative charges. Positive charges will have electric fields pointing away from them. Negative charges will have electric field pointing towards them. And so in between these plates, we're going to have an electric field that points down. Okay, and all that says is that if you have an electric field, if you have a charge in that electric field, that charge will experience a force. And so if we were to place a charge, let's say right up here, and we're going to make that a positive charge, that charge is going to experience a force that is going to point away from the positives and towards the negatives due to the electric field and let's put E field here. And if we have a force, that force is going to act over a distance, and that is actually going to be work. So if you remember that, the force applied for a certain distance, and we're in the same direction as that distance, is going to be equal to some amount of work done, and that's some energy gained by this thing, and the work is going to change the kinetic energy of the particle. Okay, and then all the way back, the way we get force is we actually put the charge in the electric field, and so if we know the E field value and we put the charge inside of it, Q, that'll give us a force, and then D is the distance, and this would be the amount of energy that you get to change the kinetic energy of the particle. Now if you were to put a particle not up here but down here, if it's positive, you still get that same force because it's in the same kind of field, but the distance that it has to go is less, which means we would get less energy out of this whenever we moved this charge from top to bottom. Okay, and so this is where the voltage comes into play, because the more voltage there is, the more electric field we can have here, and based on the distance, and the faster this thing could move across, the more energy we can give it. So voltage is actually a measure of the potential, and when we apply a charge to it, the charge would get some kind of potential energy to then be converted into kinetic energy. Last thing, if we were to not put positive charges in here, if we were instead to put a negative charge, we would simply want to be pulled the other way, because negatives want to be attracted to positives. The force wouldn't be any stronger if it's the same kind of charge or the same amount of charge, but the direction would definitely be different. Negative charges would want to go from negative to positive. Positive charges would want to go from positive to negative. So capacitors are going to hold charge here. And so if we bring these capacitor plates closer and closer and closer together, the electric field could get stronger and stronger and stronger and stronger. And now we have more reason for the charge to build up on either side. The charges are still going to fly across and get the same amount of energy, because although the distance would go down, the electric field would go up in this case. And so we would still get the same amount of energy because there would be the same amount of voltage drop. So capacitors are, by geometry, these two plates that are separated by a distance d. You usually fill something in between, and they actually do store energy. And so looking at voltage, voltage is by units, it's volts, but it's also joules per charge. Okay, so voltage is going to be joules per charge, and voltage is not energy yet if we look at the joules per charge, but if we were to multiply voltage by charge, if we knew some kind of potential difference, a change in voltage, and if we multiplied that by charge, we would then get some kind of energy. All right, and so this is where we get that electric potential energy. All right, so we need a change in voltage. Here our change in voltage would be from 100 to 0. We multiply by whatever charge we place in that if we go from top plate to bottom plate, and now we can give it some kind of energy. So capacitors actually do hold energy, and if we were to graph out the voltage and the charge stored on a capacitor, what we would get is, let's see, what would we get? If we have voltage over here and charge stored Q over here, as we increase the voltage, we'd get more and more and more charge on this thing, and it should be rather linear, I think. And so here, if we were just to look at the slope of the graph, or rather the area would actually be pretty important in this case. The area of this, whatever it is, would be 1/2 base times height, or 1/2 V times Q, and that would be equal to some kind of energy. I might as well just write it all out because we're working with multiple E's here. And then if we look at the equation for a capacitor has an equation of, well, this is how you find the capacitance, but the amount of charge stored on a capacitor, Q, lowercase or capital Q, is equal to the capacitance of the capacitor times V. And if we just plug this in down here, we get 1/2. V is going to be Q over C, and so that's going to be, actually let's replace Q instead. That's going to be CV times V again, 1/2 CV squared. There we go. And that's going to be energy as well. So the energy of the capacitor, you can even replace the V there. But 1/2 CV squared, 1/2 the capacitance of a capacitor times the voltage that's applied to it squared will give you the amount of energy that you can possibly store in that capacitor due to all the charge. So in a circuit, we can put a capacitor in a circuit. If we draw a simple circuit here, let me draw a resistor right there, right there, right there. That is not a capacitor, but for this simple circuit, our circuit would have current flowing in the clockwise direction, and so we have some resistance here. And the simple circuit with voltage and resistance would result in some kind of current here. If you were to place a capacitor in parallel, now we have the potential for some amount of charge to be stored. This student keeps on walking in here, but I'm making a video. And so this current, if we put a switch here, let's say at time 0, when we very first start off, we have current flowing through, and current's going to want to flow through whatever path it can flow through. But at time 0, this capacitor is uncharged, which means most, if not all, of this current is going to want to flow into this capacitor until this capacitor starts to become charged up with positives and negatives on the bottom. And these charges can't jump across, they just get stored there. And more charge is going to be built up, but as more and more charge is built up, this current starts to drop off. It starts to go down because there's more resistance here for it, because you can't keep on just putting an infinite number of charges there. The charges will keep on building and building and building until the voltage on the capacitor is the same voltage as the battery, because things in parallel have the same voltage, right? There's that rule. And then as that happens, that capacitor becomes a brick wall, and now the current goes back to normal, where it just flows down this resistor R. So again, in the beginning, the current flows to the right, and it's starting to fill up this capacitor. As the capacitor gains voltage, the current's going to slow down a little bit over here and then divert down into the resistor like it would normally. All right. If you were to put another capacitor in right over here, oh, I went in between dots. Oh well. If we were to put another capacitor in, what you're doing here is you're essentially increasing the surface area of the first capacitor because you put it in parallel. If you look, these two wires, this wire here, is really the same thing. And so if I wanted to, I can just move this wire down and I can connect the plates here, or I can even bring these plates together to make one really big plate. So capacitors in parallel are actually just making a bigger overall surface area. And so if we had two capacitors in parallel, we would just add the capacitance of these two capacitors together, because the current would want to fill up one, fill up the other at the exact same time until both were at the same voltage. And so if both are at the same voltage, then you have some amount of charge that fills up over here depending upon the size, some amount of charge that fills up over here depending upon the size, but it's just like having one really big capacitor instead of two. Now, in order to add these capacitors in parallel, the equivalent capacitance is just the sum of however many capacitors in parallel there are. Okay? Which begs the question, if you had capacitors in series instead, how would you add them? And if you noticed, capacitors in parallel are just like adding resistors in series. So you would kind of think that maybe capacitors in series would be much like resistors in parallel, and you'd be right. And so if we have capacitors that are all set up in series, like this, let's say this is C1, this is C2, this is C3, to make them into one capacitor, we would have to do the 1 over the equivalent the equivalent capacitance that we want, and that's going to be 1 plus 2 plus 3, although we need to put these all on the denominator and then add them. So you can definitely combine capacitors in parallel, and that's easy, just add them. If you combine capacitors in series, you would have to do 1 over 1 over 1 over, and so capacitors in series are actually going to lower the total amount of capacitance overall, which is going to lower the amount of charge able to be stored. Because if I were to start to store charge on these capacitors, and this is going to be the last thing before I end the video, if I put a positive charge here, that's going to be complemented by a negative charge there, which came from a positive charge over here, which was going to attract another negative charge here, which is going to come from a positive charge there, which is going to cause a negative charge there. So every single time that you deposit a charge on one, the same amount of charge is going to be deposited on all. Alright? So these are all going to have the same amount of charge. And so if they all have the same amount of charge, then that's going to result in less amount of charge being held overall as we look at these capacitors. So if Q is equal to CV, on the first place, the charge here and the charge here is not the same. But we can sum that up. And if we were to sum up the charge on one and the charge on the other to get the total amount of charge, if charge is equal to CV, then CV is equal to C1V plus C2V. And remember that these are in parallel, so all the V's are the same. So we can just straight up add them. Okay. Now, if we're down here, the voltages of each of these, of 1, 2, and 3, are actually going to be added together to get a total amount of voltage for that series piece, because that's how series works. And so if we rearrange this, I have V is equal to Q over C. And so if I added these voltages together, I'd have Q divided by C1 plus Q divided by C2 plus Q divided by C3. And what we said earlier was that the charge deposited on one is the same as the charge deposited on all. And so we would get the same amount of charge, which means that all these Q's cancel out. And that shows you that the way that you add capacitors together in series is to do the 1 over thing. Alright, I'm going to end that here. There is more to do with capacitors as we solve circuits, but that is just an introduction. And I'll see you later.